First question. So we're going to talk about how we would change the frequency. Change the frequency. The only thing that you have to change is changing the source. The frequency is determined by what creates the wave. So what we have to do is change the thing that's creating the wave. In order to change the wave velocity, we have to change what the wave is moving through. We call that the medium. When we change the medium, the wave velocity changes. The next thing that we're going to look at is the wavelength. The wavelength's a little funny. It depends on the frequency and the velocity. So if you change the frequency and you change the velocity, you're going to be able to change the wavelength. Next thing we have is the amplitude. Amplitude has to do with energy for a wave. So we're going to have to change the work done in creating the wave. Think of shaking a wave on a string. The more you shake it, the bigger the wave is going to be. That's what the amplitude is all about. All right. Number 2 shows two waves meeting. So what we're going to do with the two waves meeting thing, this is our constructive or destructive interference. Here we have constructive interference. Each wave disturbs the medium by lifting it up an amplitude of 2A or A. When they're in the same place at the same time, they're just going to lift the amplitude up a total of 3A. Then, after that happens, they pass through one another. As if nothing happened. And they continue moving. Okay. Now, for number 3, part A doesn't matter that much to me, but in general, just so that you know it, when we're looking at a graph like this, and I want the y as a function of time, it's going to be the amplitude of the wave times sine of 2 pi times the frequency times time. That's going to give me y as a function of time. I don't care so much about that formula, but I want you to be able to find the things that are in it. So for this wave, the amplitude, we can read it right here, is 4 centimeters. And in order to get the frequency, it's waves per unit time. And if I look at this, if we look at what's happening here, we get one whole wave in 0.2 seconds. So the frequency comes out to be 50 hertz. So if I want to look at y as a function of time, we'll just plug those things in. 4 sine 2 pi times 50 hertz, so that's 100 pi times t. Again, I don't think that's terribly important. On part B, calculate the wavelength of the water waves. That might be a little bit different. So for part B, we can totally do this. Wavelength is velocity over frequency. They tell us that the velocity is 10 meters per second. We just found the frequency to be 50 hertz. So that wavelength comes out to be 0.2 meters, which is 20 centimeters. Okay, that's just some basic wave stuff. It's a little bit of a review of things that we've done before. So let's look at number 4. This is where we start getting into things that we've done recently. So draw a diagram showing all the possible paths that the incident light could follow. Some will be reflected at each interface. So what we're going to do is different colors, I guess. We'll do the transmitted stuff first. We'll make the transmitted stuff blue. So, glass has the N of 1.6. Water has an index of refraction of 1.3. So we're just going to go through the paths. Now as we turn into the water, we're slowing down. As it slows down, it turns towards the normal. So let's write this down. So as it enters the water, it slows. And it turns toward the normal. Then it enters the glass, so we have a new normal now for the glass. It's going to slow down again. So it's going to slow and it's going to turn towards the normal again. So we are at an even steeper angle in the glass. So it speeds up as it goes from glass to air. And as it does that, it goes away from the normal, and all of our refraction is undone, and we're back to the 30 degrees that we had before. That's just the refracted stuff. We also have to do the reflected stuff. So it's going to reflect at the first interface, and it's going to have the same angle. So good, that one's 30 degrees. It's going to reflect at the water interface, and then it's going to come back out, refract. It's going to reflect at the glass-air interface, same angle that we have up there. It's going to refract, and then it's going to refract again. So now we need to find out all of our angles. So we'll move over here. So for air to water, we're going to use Snell's law. N1 times sine 30 is equal to N2 times sine of theta 2. So that's 1 times the sine of 30 equals 1.3 times the sine of theta 2. So theta 2, the one that we're after, is sine 30 divided by, to find the angle, we got to do sine negative 1 of sine of 30 divided by 1.3. That makes theta 2 come out to be 22.6 degrees. So this angle right here is 22.6 degrees, which makes that angle also 22.6 degrees, which is our next thing that we're going to deal with. That is water to glass. So for water to glass, we have water into sine theta 2 is equal to glass N3 sine theta 3. So we'll plug in everything we know. 1.3 sine of 22.6 divided by 1.6 is sine of theta 3. So theta 3 is sine negative 1 of all that. Theta 3 comes out to be 18.2 degrees. So this is 18.2 degrees. That is 18.2 degrees. Good deal. And then, just to show it, glass to air, so that's N3 sine theta 3 is equal to N1 sine theta 1. So 1.6 times the sine of 18.2 is equal to 1 times sine theta 1. So theta 1 is sine negative 1. 1.6 sine 18.2. Giving me theta 1 that is close enough to 30 degrees that we can just say it's 30 degrees. So here, on our way out, we are back to 30 degrees. Now, reflected angles. If this angle is 26.6, that angle is 22.6, and this reflected angle is also 22.6. And then when we refract out, air to water, it's 22.6 and 30 degrees. So that's good news. In the glass, we said this was 18.2 degrees. So that's 18.2 degrees. The reflected angle has to be 18.2 degrees. Then when we go back into the water, between water and glass, it's always going to be 18.2 and 22.6. So this is 22.6. And then that comes out to be 30 degrees. And so we're done. That was a lot. Now that's not hard, that just takes some time. Okay, so that was just the angles in which medium, the water or the glass, is total internal reflection possible. Sorry about that. So, it's only possible in the glass. Total internal reflection happens when moving from a slow medium to a fast medium. The only time that happens is when the light is leaving the glass going into air. That's it. Calculate the speed of light in each medium. So we'll do part D right here. So air, water, and glass. So in order to do this, in order to calculate the speed of light, what we're going to say is that the index of refraction is the speed of light in a vacuum divided by the speed of light in the substance. So air, N is equal to 1. That means the velocity is equal to c, or 3 times 10 to the 8th meters per second. That's the speed of light. In the water, the velocity is going to be N times, water, the velocity is going to be c over N. So the velocity is going to be 3 times 10 to the 8th meters per second divided by N, which is 1.3. So that velocity comes out to be 2.3 times 10 to the 8th meters per second. In the glass, the velocity again is c over n. So it's going to be 3 times 10 to the 8th divided by 1.6. When we do that, the velocity comes out to be 1.9 times 10 to the 8th meters per second. Okay, let's move on. You can feel free to pause this at any freaking time that you would like. Any time that you would like. Sorry, I thought the recording had stopped. The student is given a converging lens. He's asked to create a real image that's 3 times the height. Describe how he would do that. Okay, so let's look at question 5. 3 times the height of the object using just this lens. We need 3 times the magnification. So, we know that magnification is image distance over object distance. So that tells me that since we want 3 times the magnification, the image distance has to be 3 times the object distance. So, we need to find the object distance. We want to know where to put it. So 1 over SO is 1 over SI is 1 over F. Okay. This is what we've got. 1 over F equals 1 over SI plus 1 over SO. But I know that my image distance is 3 times my object distance. So I can substitute that. So if I want to add those together, I get 1 over F is equal to 4 over 3 SO. And if I wanted to, we could do a little cross multiplication. And we get SO is 4 times the focal length divided by 3. So 4 times 6 centimeters divided by 3. So we get 8 centimeters. We left everything positive because it was a real image. Now, that's my math. That's not telling me how we need to create it. So, we're going to put the object to the 8 centimeters to the left and the image will form 3 times as far away, so 24 centimeters. 24 centimeters to the right of the lens. So if we wanted to draw all of that, we put our lens right there. And if we said that's my focal point and that's my focal point, we need to put our object here. Our rays would look like in parallel out through the focus, in through the focus, out parallel, and it's very close to what we need. I obviously had a problem drawing. No, you know what? Let's make it right. There we go. It's 3 times bigger, and it's real. Okay. Number 6, explain how diffraction occurs and what conditions are necessary for diffraction to occur through a particular barrier. 6, we just need to kind of define diffraction. So diffraction is the bending of a wave through a barrier. To make it happen, a wave passes through an opening in a barrier. By treating every point on the wave as a point source, only points near the barrier pass through. If the opening is small, compared to the wavelength, a plane wave becomes circular. That's kind of our condition for it. Now, if we're going to look at that picture, here's my opening. Send a wave towards it. Since each one of these is a point source, the only point source that we're going to have actually making waves is right here. So that point source is going to kind of curve at our edges, and our wave comes through like this. If the opening is too big, then that doesn't act like just one point source, it's multiple point sources, and we get another plane wave that passes through. All right, number 7, we have a concave mirror. We want a virtual image with that. So here's my mirror. Here's my focal length. So if I want to get a virtual image, the image distance has to be less than the focal point. So if we draw our rays, because we're showing this with a ray diagram, we come in parallel, out through the focal point. We come in as if we're going through the focal point, and out parallel. These two things don't meet in real life, so we have to trace them back to where they do meet. So the traced back ray meets behind the mirror. That gives me a negative image distance. All right, number 8, we have a 3 centimeter tall object, 4 centimeters in front of a diverging lens. Calculate the height, indicate if it's real or virtual, indicate if it's upright or inverted. It's a diverging lens, so it's going to be virtual, and it's going to be upright. If we put the thing into water with no other changes, the image would be the same. It would be the same because the refraction is due to curvature. Now, to calculate the image height, 3 centimeter tall object, 4 centimeter in front of a diverging lens, whose focal length is 8 centimeters. So, what we need is the image distance, 1 over the focal length minus 1 over the object distance, but the focal length is also negative. 1 over 8 minus 1 over 4. You have 3/8. 1 over SI is negative 3/8. So SI is negative 8/3. That makes the image height, the object height, times SI over SO. So negative 3 centimeters times negative 8/3 over 4. The 3's go away, and that image height comes out to be 2 centimeters. It's upright, it's going to be positive, and it's smaller than our actual object, which is what we expect to see. Okay. Figure below shows a model of an electromagnetic wave. That's a fancy way of just saying light. An electromagnetic wave is a disturbance of an electric field and a magnetic field, but this is the wave. It's the interaction between the two. They act at 90 degrees to each other. But the velocity of the wave is forward. Electromagnetic wave is created by basically moving a charge, accelerating a charge. Anytime we can create an electric field and a magnetic field at the exact right rate, we get an electromagnetic wave. Or when we accelerate charges. Electromagnetic waves can be polarized, but sound waves cannot be polarized. Sound waves are compression, directionless. Well, they're not directionless. Sound waves are compression waves. Electromagnetic waves have ups and downs and side to sides. We can filter that out. Basically, it's the difference between a transverse wave and sound wave being a longitudinal or compression wave. Describe how you would measure the wavelength of a laser, the focal length of the lens, or a index of refraction of a piece of glass. All right, so A you're going to shine the laser through two small slits that are close together onto a screen. You're going to measure the distance to the screen, L. You're going to measure distance to the first bright spot, Y. Those are the things you're going to measure. And then you're going to change L and repeat multiple times. So physically, what's going on as we do that? You have your two small slits and your screen, and you're going to get a bright spot here and a bright spot here. That bright spot happens because of the difference in wavelength. So you get a bright spot in the middle because each wave had traveled the same distance. Here's our Y. Each wave here travels a slightly different distance. The difference in that path length is lambda. The difference between the two slits is d. The difference in the path length is d sine theta. It's equal to lambda. But through some very fancy trickery with math, this angle, pardon me, and this angle are the same. So
moving ground choreography experience 1 is starting at 3:45 in G216. Please look up all of your items and be on time. Thank you.
All right, so to do the focal length of a lens, pick a different color. Do this right here, focal length. Okay, to find the focal length of the lens, set up the candle, the lens, and a screen. Find image. Once we find that image, we're going to record SO and SI, the image distance and the object distance. Repeat for multiple SO and SI. And then we're going to graph. So, for our graph, our equation is 1 over F equals 1 over SO plus 1 over SI. 1 over SI is equal to 1 over SO. Sorry. 1 over SI is equal to 1 over F minus 1 over SO. So we're going to want to make these our Y's, and those are going to be our X's. When we make that graph, 1 over SI, so we're going to graph the inverses, 1 over SO, we're going to get something that looks just like this. So when SO is 0, that is 1 over our focal length. When SI is 0, that's 1 over our focal length. When SO is 0, that's 1 over our focal length. So the intercepts here are 1 over the focal length. Now, the last one that we're going to do the explain how for is to find the to find the index of refraction of our material. We have our material. Here's our normal. Shine a light into the material. Theta incident, theta refracted. So shine the laser into the material. Measure the incident angle and the refracted angle. Repeat multiple times. And lo and behold, we're going to make a graph. So we know that sine theta 1 is equal, N1 sine theta 1 is equal to N2 sine theta 2. So sine theta 1 is equal to N2 sine theta 2. When we're making our graphs, we come over here and we say, okay, that is our y, that is our x, and that is our slope. So we'll come over here and we'll graph sine of our incident angle on the y-axis. We'll graph sine of our refracted angle on the x-axis. And the slope is going to be equal to the index of refraction of our little piece of glass or plastic or whatever we're using. Those are the three things we can do for that. We did 2 of those labs. All right, number 11, we're going to do a diffraction problem. So light of wavelength lambda hits 2 narrow slits, and this is what we see. At point P, there is a minimum. Determine the path length difference between the light arriving at this point from the two slits. So, multiple ways that we could do this, but they give us lambda. So, from here to here, the delta L, we'll just say the path length difference is 0. From here to, well, here the first minimum, delta L has to be equal to 1/2 of a wavelength. Because at that point, we're getting destructive interference. Destructive interference happens when we are at the same place and we are out of phase. So that's the first one. The next time then we get here, my path length difference should be 3/2 of a wavelength. So at that point we are 3/2 lambda off. That's one way we could do it. The other way is just kind of based on the geometry of the situation. And we talked about this with our last little thing. So we have L, we have Y. We have theta. Okay, so what we get here is that tangent of our angle is L over Y. So essentially the tangent of this angle, because it's very small, is oh. Okay, so tangent of that angle, sorry, tangent of the angle is L over Y. The path length difference from here to here, this is my path length difference, is d sine theta d sine theta is delta L, so sine theta is delta L by path length difference divided by the separation of the slits. Because this is a very small angle, these two things are equal to each other, so L over Y is equal to delta L over D. So L times D over Y is equal to my path length difference. And so what we get is L, 5 meters, times the distance separating these two things, 2 millimeters, 0.002 meters, divided by Y. And Y is from 0 to right in between. I want to say 1.8 millimeters, 0.018 meters then. So that makes apologies, I wrote a couple things wrong. So tangent theta is Y over L, not the other way around. We got Y over L. So that changes this to 0.018 times 0.02 divided by 5. So that makes my path length difference equal to 3.6 times 10 to the negative 4th meters. That's my path length difference. Now determine the wavelength lambda of the light. Well, we said over here that my path length difference had to be 3/2 of a wave, because that's where we have our negative interference going on. So lambda is equal to 2/3 of this distance L, 3.6 times 10 to the negative 4th meters. So lambda comes out to be just about 2.4 times 10 to the negative 4th meters. Briefly describe what would happen if we performed this underwater. Which has an index of refraction greater than 1, so the velocity would decrease. All right, so the velocity goes down, which means the wavelength goes down. And if the wavelength goes down, the pattern would compress. The Y's get smaller, so that they get closer and closer together. If we cover one of the slits, we just see single slit diffraction. And when we get that, there is sort of one really big central minimum and then two smaller ones out to the side. If the slits are moved farther apart, that means D increases. If D increases, we have this relationship Y over L equals delta L over D, where that delta L is like M times lambda over D. So if I make D get bigger, Y gets smaller. So the peaks in the pattern get closer together. Because everything else is going to stay the same. All right, that is our review. Good luck.